Hi, in this video we're going to learn how to solve problem 1.3 in the Griffiths and Shroeter Introduction to Quantum Mechanics 3rd edition book. Problem 1.3a asks us to find the constant a, and we could do this by using the relationship that the integral from negative infinity to infinity of a probability density function must equal 1, since the total density must be 100 or 100%. So we can just plug this in, negative infinity to infinity of a e to the power of negative lambda x minus a squared. And we could do use substitution in order to simplify this. And what we get is the integral from negative infinity to infinity of e to the negative lambda u squared du. And the reason why the bounds of integration stay the same is because plus or minus a constant a does not change whether it is infinity or negative infinity. So that's why the bounds stay the same. And this is a Gaussian integral. And in the back of the textbook, there is a Gaussian integral relation that says that the integral from 0 to infinity of x to n e to the negative x squared over a squared dx is equal to the square root of pi 2n factorial a over 2 2n plus 1. And this is the relationship for when the power of x here is not odd. So in this case, there is no x in front, so the power of x here would be x to the 0, which would make 1, so there won't be an x in front here. That's why we have to use this relationship. So then now we have to also match this integral to this here, and the only thing that doesn't match is the bounds of integration, because this one is from 0 to infinity while this one is from negative infinity to infinity. But we can turn this integral into this by multiplying a 2 in front and then just doing the bounds of integration from 0 to infinity. And the reason why we could do that is because this function here is symmetric about u is equal to 0. And because it is symmetric about u is equal to 0, we could just take the integration from 0 to infinity and then multiply that total value by 2. So now we just have to match this here with what we see here. So we know that n must equal 0 since there is no x in front, and a must equal 1 over the square root of lambda, because whenever we put 1 over square root of lambda here, the square root goes away, so it will be 1 over lambda, and then the 1 over lambda on the denominator will go on top, which is exactly what we have here. Now we could just evaluate this based off of this relationship here, and what we get is the square root of pi of 0 factorial, 1 factorial, and then it'll be 1 over 2 lambda square root of lambda to the power of 1. But we also have to remember that there is still a 2 and then times a, so then we have to multiply this by 2a as well. So then now what happens is these go away and these are just 1, and then these 2's cancel, and then what we get is a square root of pi over lambda must all equal 1. So we know that a must equal the square root of lambda over pi. Problem 1.3b asks us to find the expectation value of x and the expectation value of x squared and the standard deviation. So we could start off by finding the expectation value of x, and this is equal to the integral from negative infinity to infinity of x times the probability density, and we just plug in. And we could use u substitution again. So u is equal to x minus a, du dx is equal to 1. And x is equal to u plus a. So then what we get is the integral from negative infinity to infinity of u plus a, since we just replaced this x with u plus a, square root of lambda pi of e to the negative lambda u squared du. The next thing we'll do is split this integral into two, and we do that by distributing this here into u and then a. And we will also pull out this constant, square root of lambda over pi. So the first integral will be just u e to the negative lambda u squared du. And the second integral will be a e to the negative lambda u squared du. And a trick that we could use is that we know that this must equal 0. And the reason we could do that is because e to the negative lambda u squared is an even function, while u is an odd function. And the integral of an odd times an even function is always 0. And it's because, for example, if we draw out what e to the negative u squared looks like, it looks something like this, and it's symmetrical about u is equal to 0. And if we and then u, the function u, just looks something like this. So all the values on the right side of this dotted line will be positive, while all the values on the left side of this dotted line will be negative. But they will still be symmetrical once both these functions are multiplied. And eventually they just integrate to 0. Now we just have to worry about this integral here. And we again have to use the Gaussian integral identity as we used before, right here. And in order to do that, we have to first turn this integral from 0 to infinity, like we did before. So it will be the square root of pi, lambda over pi, a times 2. Remember, we have to multiply by 2 if we want to do from 0 to infinity, of e to the negative lambda u squared du. And then this here, n will equal 0, and a will equal 1 over the square root of lambda again, so that n and a are the same since there is no x in front. So the expectation value of x will be square root of lambda over pi a times 2 times square root of pi 0 factorial 1 factorial of 1 over 2 square root of lambda to the power of 1. So we see that many things cancel. These 2's cancel, these pi's cancel, these lambdas cancel, and what we eventually get is that the expectation value of x is just equal to a. And this makes sense because if we just look at the probability density here, we see that x is centered at x is equal to a because it's shifted by a here. So we could continue with this problem by solving for the expectation value of x squared, and it's the same thing as before. The integral from negative infinity to infinity of x squared times the probability density, and we just plug in for the probability density. e to the negative lambda x minus a squared dx. And then we use the same u sub that we did before. Bounds stay the same. And we replace x with u plus a. And if we factor this term out, what we get is that the integral from negative infinity to infinity of u squared plus 2 2au plus a squared, and all this is multiplied by e to the negative lambda u squared du. Now we just split up these integrals. And we see again that this will turn into 0 because this is an even function while this is an odd function. So we only need to worry about this integral here and this integral here. What we could do is solve for this right integral first, since it is easier. However, we really don't even need to solve for this because we have solved an integral pretty much the same as this one above here, right here, except that this is an a instead of an a squared on the bottom. But since this is a constant, we could just multiply the final value by a. So we know that this must equal a squared. And now to solve for this integral will take a little bit more work. So we have to use the Gaussian identity again, and we could use the same one that we used before because u, the power of u, is 2. And even though this is not x, it doesn't matter. It's just a name for a variable. So then we use the same reasoning that we did before. We have to multiply by 2 in front in order to convert this integral to the correct form. And then now, instead of n being equal to 0, it is now equal to 1. Because if you recall the identity above, in order for x to have a power of 2, n must equal 1. So then a will be the same since this part never changed. And what we get is square root of lambda pi 2 times the square root of pi. Now it's not 0 factorial, but now it's 2 times 1 factorial with 1 factorial on the bottom. And this will be 1 over 2 square root of lambda to the power of not 1, but now it's to the power of 3. We could work on simplifying this by canceling out the pi's. And these 2's will cancel out with this 2 on the bottom, but we have to be careful because this 2 on the bottom is cubed. So there will still be just 1 2 on the bottom. And this lambda will cancel out with this lambda on the bottom. But once again, we have to be careful because this was cubed. So we're just left with a lambda on the bottom. So now we know that the expectation value of x squared is equal to 1 over 2 lambda plus a squared. We have to remember to add it with a squared as well, because there was this integral on the top here. And now we have all we need to find the standard deviation, because we know that the square of the expectation value of x is equal to a squared. And in order to get the standard deviation, it's just the square root of the expectation value of x squared minus the square of the expectation value of x. And what we end up getting is that these a squares cancel out, and it's just the square root of 2 lambda. 1 over the square root of 2 lambda. Problem 1.3c asks us to graph the probability density, and we'll just assume that there's a random point A here, and we know that A is what determines the symmetry point of the probability density, since it shifts where this value here will be equal to 0. We know that it's symmetrical about A and that it's a Gaussian, so it's going to look something like this. And the point at A, which is the maximum value, will be equal to just square root of lambda pi, because this here will be 0. And then when this is 0, this entire thing would just be equal to 1. And the standard deviation, we could plug that in. So it's going to be 1 over the square root of 2 lambda is equal to lambda over pi e to the negative lambda. And then in order just to get an idea of what the standard deviation will be, we'll just assume that a is equal to 0. It will simplify the calculations a lot. And then the square root will go away since there's a square here. It will just be 1 over 2 lambda. These lambdas will cancel. And what we end up getting is e to the negative 1/2, which is around 0.61 square root of lambda pi. So if we just look at something that is a third of the way down from the peak, which is, let's just say it's somewhere right here, this is where the standard deviation will be. So this will be a minus 1 over square root of 2 lambda, and this point will be a plus 1 over the square root of 2 lambda. And then this point will be 0.61 square root of lambda pi. I hope this video helped with problem 1.3, and if there are any questions, feel free to leave it in the comments. Thank you.